This question for exam practice is like the others, a little more difficult numbers to deal with. But I'm going to go over this showing every detail that and about every question that we could be asked, or things that we could do about this. So we have, as we've had previously, a 100-meter cliff. And we should set up our coordinate system. So we'll make the starting height 0, and we'll make the ground minus 100. And so again, when this projectile flies, we are going to translate it a little bit along the x-axis like this, even though it would truly go straight up and straight down. But since it would be on top of each other, it would be difficult to see. So I'm going to translate it a little bit for us to see what's going on. There are some factual things about this that we should remember. When something is thrown upward, there is symmetry on the path up and down, so that this time will be equal to this time. The time up equals the time down. And that this V0 it's launched up with over here will be minus V0. So those will be the same. Those are just some things to know. And that this V0, the negative V0 over here, which we know will be minus 16, that the time it takes to go from here to here would be exactly the same as if it were thrown downward at minus 16. So that's just some things to remember about this type of vertical projectiles that are thrown. So we're going to start out by getting some estimates of a number of quantities and critical values by using our average velocity table. So we'll take our time with this, because it's going to allow us to check all of our answers to see that they make sense. So we have 0, 1, 2, 3, 4, 5, 6, 7. And the next quantity we are going to determine is the instantaneous velocity. And then the quantity after that is the average velocity. And after that, we will have the displacement, delta z. Just a reminder where these come from. So this is just a simple count. This column is what we're doing is we're basically taking the velocity above it and we're subtracting 10 meters per second. So in the beginning, we are told that the initial velocity is positive 16. So in determining that, we would subtract 10, which would give us 6. We would subtract 10, which would give us minus 4. Another 10 would be minus 14, minus 24, minus 34, minus 44, minus 54. Now, some of you have asked, how is it we know how much time to build into the table? Well, the answer to this is just like when we ask the question, how many trials do we make when we are collecting data? We know we've collected enough trials when the running mean stays the same. In the same sense, we know we have enough time in our table when we've gotten to the end point. And the end point in this case is a delta z of minus 100. So our approach should be then to work across the table as much as we can. So let's work across. And most of the examples in class, I've been focused on explaining to you how to get the numbers in each column. At this point, we should go across so we can, save our time. And maybe just add one other thing with this case. This column is v equals at plus v0. So the instantaneous velocity here, or the average velocity for the first column, is 0. No time has passed, so having an average velocity has no meaning. So the change in vertical is minus z. And remember, we're looking for when we get to minus 100. Well, the average velocity of 16 and 6. These guys, the average velocities come from this equation, the final plus the initial over 2. So 16 plus 6, 22 divided by 2 is 11. And then 16 plus a minus 4 is 12, divided by 2 is 6. But we should, just take a pause here to calculate the delta z. So here we have a position of 11. Here we have a position of 12. So we can see we're on our way up in this case. Okay, we've only gone up at this point. Our next average velocity is going to be 16 and 14, excuse me, is 2, divided by 2 is 1. And of course, we see that pattern of minus 5, minus 5. 1 times 3 is 3. Oops. So now in interpreting what's going on here, we have gone up and we're clearly down. And we have been down because the velocity is negative. So at some point here, either between 11 and 12 and 3, we had our max height. It could have happened beforehand, because if you notice we're at time 2 seconds, we're already on our way down. So it suggests it's really in here. Between 1 and 2 seconds is max height. But we're not at minus 100 yet. So we go to the next one in the table, and we've got minus 4. 1 minus 5 is minus 4. Minus 4 times 4 is minus 16. Must keep going. And our next one is minus 9, which gives us minus 45. And then we have minus 14, which gives us minus 84. And we still haven't gone far enough. So we go to minus 19. And sure enough, we get to minus 133. So that tells us we have impact in this range. So 100 is 16 away from 84 and 33 away from 7. So it's closer to the 6 than it is the 7. So we might say that the time is like 6.3. And the instantaneous velocity we might say is 48. And that's when it would be at minus 100. So we've estimated a number of things here in the table. We've determined when the max height would occur, somewhere between 1 and 2 seconds. We have determined the time it should take to hit the ground, which is about 6.3 seconds, probably plus or minus 0.2. Probably not going to be off by more than that, because we know it's not as much as 6.5. It's not halfway. We've got an instantaneous speed of about 48. So we've figured out a lot just using our average velocity table. The next step would be for us to write equations for our instantaneous velocity, which is v equals at plus v0. The acceleration is minus 10, that's gravity, and the instantaneous velocity is plus 16. So this is our model that will give us the instantaneous velocity for all the time that this thing is in the air. So if we were to want to know the time it hits the ground, well, we don't know the velocity or the time it hits the ground, so we can't get the answer from that equation. Now, if we move on to our position equation, z equals 1/2 at squared plus v0t plus z0. Acceleration's minus 10. Our initial velocity is 16. And our initial position we set at 0. So we have a model of minus 5t squared plus 16t. And so that is the position of the rock. The position of the ground is minus 100. So from there, we go into Desmos, graphing calculator. We plot this, we put that in, and then we look for when the value is minus 100. And we find out that that time is about 6.349 seconds. Now, of course, we're going to check our table to see if that makes sense. And lo and behold, we estimated it was about 6.3. So we're pretty good. Now, we expect the impact velocity to be about 48. Take that in and put it up here. We use the unrounded value, so v equals minus 10.6.349 plus 16, and that gives us 63.49 minus 63.49 plus 16, which works out to be minus 47.49, which to two significant digits is minus 47 meters per second. And lo and behold, we estimated from the table it would be about 48 meters per second. So our analytic solution matches our predicted or estimated solution. The next thing we can do is try to determine the maximum height. Well, let's see. We've got two equations. We've got our blue equation, v equals minus 10t plus 16, our model of the velocity. And we have our model for the position, z equals minus 5t squared plus 16t. And this is at the top, or max height. Well, what do we know about when it's at the max height? We know it's about 1.6 seconds, and we know it's probably a little bit bigger than 12 meters. And we know that from our table. We already figured that out, that it's already on its way down at 2 seconds. It's on its way down at 2 seconds. So it must already have reached its maximum. And if the biggest number in the table is 12, it must have been, as it had to have a velocity of 0. So sometime before this must have been bigger than 12. So let's see here. Well, what we want to know is when at the top, we know the velocity is 0. And that's a key thing for us to know the velocity is 0. So 0 is the velocity minus 10t plus 16. So 10t equals 16, and that means that t equals 1.6 seconds. And if we go back to the table, we estimate it should be between 1 and 2, so that matches. And now we can find out the maximum height. What is the position at 1.6 seconds? And we find out when we use our calculator on that we get 12.8 meters. And to two significant digits, that means it's 13 meters. So we said 1.6 seconds, which is what we calculated, and we said 13 meters. So we have analytically solved every one of the important questions we could ask about this, and our analytic solutions match the table. The last thing we want to do here is look at the graphs of these things. So what I'll do next is we'll start out with our velocity time graph. And so here's our velocity in meters per second, our time in seconds. Here's our 0 value, so that means this is quadrant 1, and this is quadrant 2, quadrant 3, quadrant 4. And we can use our OYXIRGA so we don't make any mistakes. So our origin, we've specified that. Our y-axis, we've specified that. Our x-axis, we specified that, and next comes our intercepts. So we want to ask when the time, or the x-axis, is 0. At time 0, what was the velocity? Well, v0 is 16 meters per second. Now, we happen to know some other values. We know it reaches the top in 1.6 seconds. So if we come over here, 1.6, we know the velocity is 0. Oh. And we know in another 1.6 seconds, it comes back down to its original height. So that puts us at 3.2. We're at minus 16 seconds. And so we've got an x-intercept and a y-intercept. Now, what can we read off this graph? We can read velocity and time. The gradient, or the slope, is delta v over delta t, which is the definition of acceleration. And for this problem, the acceleration should be minus 10. the acceleration caused by gravity is constant. So I have a constant slope. I draw my line like so. The area is v times t, meters per second times seconds is meters. So it is the delta z, the change in height. So we have this critical value, which is 1.6 seconds. We have this critical value, which is 3.2 seconds. And we know overall it hits the ground at 6.3 seconds. So that's 3, 4, 5, 6.3 seconds. Impact. And we happen to know the velocity is minus 47. So let's analyze the area here a little bit. What we know is we've got this area here. And when the velocity equals 0 at 1.6 seconds, the height is 13 meters, 12.8 meters. So we know this is positive 12.8. And after another 1.6 seconds, we're back at the same height, which means that this has an area of minus 12.8. So at this point, 3.2 seconds, the total area should be 0 because total area is the displacement, and it's exactly the same height as it was. So now what we know from 3.2 to 6.3 seconds is that the object, the rock, is traveling downward, and at 6.3 seconds, it hits the ground. And we know that it hits the ground when the position is minus 100. So the area in this case is minus 100, and that would correspond to a value over here of minus 47 meters per second. That's what the y-axis value be, minus 47. So that's how this motion plays out on a VT graph. Now let's look at a ZT graph. So we have our time in seconds. We have our position Z in meters. And if we do our OYXIRGA over here, I'll write it in the margin over here, OYXIRGA. Well, let's see. The origin we've got is 0, 0. And that origin, we know where it is. Our y-axis is the position. We've got that. X-axis, time in seconds. Our intercepts. All right. So at time 0, where is this thing? It's at a position. It's at a position of 0, we said. And we know after 1.6 seconds, it's at its maximum height, which was 13. 12.8 or about 13. So it's about there. And after 3.2 seconds, it's back to the same height. And we know that at 6.3 seconds, it's at minus 100. Minus 20, minus 40, minus 60, minus 80, minus 100. 4, 5, 6.3 seconds, minus 100. So we said that the maximum height is at 12.8, 1.3 seconds. So we have a symmetrical parabola. Oh, I put that in the wrong place. I put it at about 1.3, not 1.6. A little more than halfway. Am I doing it? It's up here. And so we get our maximum. Oops. Hard to draw that. Like this. And annotating this, now we know this time here is 1.6 seconds. We know this point, this is 1.6 seconds. This entire thing to here is 3.2 seconds. We know this maximum height is 12.8 meters. And we know this time here is 6.3 seconds at a height of minus 100. So we've got our intercepts here, both when it starts at 0, when it returns to 0. We can read off this graph the position and time. The gradient is delta z over delta t, which is the velocity. And so if we were to analyze the velocity, we could say, oh, that's big. It's decreasing, and at the top, it's 0. And then it's increasing again throughout. And we know that when it makes an impact, the slope must be about minus 47. The slope is minus 47. Now the area in this case, z times t, meters times seconds. Meters seconds is not a useful quantity to us, so it doesn't tell us anything useful. And that's how we can analytically and graphically and with our average velocity table completely understand the vertical motion of that vertical projectile.